Related to energetics, right? Just energetics. I'm not going to do decomposition questions. This is the same question we did earlier. Yeah, we're gonna try and do this question. So this is a similar question that we did earlier, which is that solubility of hydroxides, right? We talked about solubility of hydroxides, and that was what was it about? It was this one. Okay, down the group, the cationic radius increases. Your lattice energy, breaking the lattice and then hydrating the ions. Both of these values will decrease because bigger ions, they form weaker bonds. But since it's becoming more soluble, so that means breaking the lattice probably becomes easier down the group. So that decreases more compared to this, or this decreases less compared to this. So your enthalpy of solution becomes more exothermic down the group. Okay, so this was the standard answer to this question. So we're going to try and solve this question now. He's asking you, he's given you this data over here, which is here. And he's asking you to figure out the enthalpy change for reaction number 1, which is this. Now, when you're given enthalpy of formation of reactants and products, when you're given this, the formula of enthalpy change is simple. This is AS, enthalpy of formation of your products minus the enthalpy of formation of your reactants, right? So can anyone tell me how would I apply this? They've given me the enthalpy of formation of carbon dioxide. That's given. They've given me the enthalpy of formation of water as well. That's given. They've given me the enthalpy of formation of barium carbonate as well. So I know the enthalpies of formation of my products. But the thing is, they've not given me the enthalpy of formation of barium hydroxide. That is not given. So this thing over here it's not given in the table above. So if I know this, then I can use the formula and I can figure out the enthalpy change. So can anyone tell me how do I find the enthalpy of formation of barium hydroxide aqueous?
And we go from the barium and hydroxide ions to the barium hydroxide, like cascade those together.
Yes, exactly. So the thing is that when you talk about barium hydroxide aqueous actually means that it's dissociated. It means you got barium ions aqueous and you got two OH ions aqueous. They're separate. Now you're given the OH ion enthalpy of formation, you're given the barium ion enthalpy of formation, so you can use that formula, which is, so I'm just going to do the math. The enthalpy of the reaction will be, try and do this quickly, product enthalpies of formation, which is barium carbonate, which is minus 1216. And the other one is H2O, that's minus 286. So product enthalpy of formation minus the reactant enthalpy of formation, which is barium ions, that's minus 538. Then you got two OH ions, that's minus 230 times 2. And then you've got CO2, which is minus 394 times 1. So what do we get for this? Ibrahim, kya hai iska? Anyone else, Jody? Zaina, what's the answer to this?
Sir, minus 110.
Okay, so you're getting minus 110.
0.
Okay. Can somebody double check this one as well? Are we getting this?
Sir, मैं कर रहा हूँ.
So I'm just going to write reaction number 1. That is minus 110 kilojoules. Okay. Is this the value? Sure?
Yeah, I got the same answer.
Okay.
जी sir.
So we're gonna move on. Okay, that's the first question, product minus reactant side. And we found the enthalpy change. Now moving on to the next part of the question. So the next part of the question is that so the next part of the question is He says there's a reaction number 2 and its enthalpy change has already been calculated, right? So he's asking you to figure out the enthalpy of formation of, so there's reaction number 2 and the enthalpy change is already known. And they're asking you to figure out the enthalpy of formation of HCO3 minus 1 aqueous, right? So that means the answer is already known. So you need to find so if you know the enthalpy of formation of the reactants, which is given in the table, and barium hydrogen carbonate is aqueous, that means it's going to be in dissociated form. It's going to be barium ions and 2HCO3 minus 1 aqueous ions, right? So it's going to be dissociated. So my formula will be that it's the same formula. It's going to be the enthalpy of formation of barium ions, which is given in the table previously. What was the value? It was minus 538. Okay, so this one is, the first one is minus 538. Then you've got, this is X. We don't know what hydrogen carbonate is, so that's 2X. So that's my product. Minus my reactant, which is barium carbonate, carbon dioxide, and H2O. So what are those values? Those values are, for barium carbonate, it's minus 1216. I'm just going to add it over here. And then I had carbon dioxide and water. Water is given as minus 286. And I need carbon dioxide as well. That's given as minus what? Minus 394. So going back, you get this one. And the answer is already known. The answer they've told us is going to come out to be minus 26. So quickly find out what X is. Okay, what's going to be your X? It's going to be minus 26. And then plus 394. And then plus 286. Okay, so it's going to be plus 286. Okay, try and solve this, okay? What do you get for the answer for this one? ठीक है ये clear है this is just enthalpy of formation of product minus reactants and that's your answer over here. Anam, what Akshita, are you doing this one?
I got X equals 192, negative 192.
Negative 192, right? So
Yeah.
so that's that's negative 192. That's what you're getting. Okay, which I think is, can somebody double check this one? And let me just open the marking scheme as well for this 1 second. So this was question 10. So this was question number 10. So for this, the first one was minus 110, the second one is, I mean, they've given minus 692.
Yes, sir. I also got minus 692.
Okay, so again, was it minus 192 or minus 692? Zaina?
I'm checking my calculator history right now, but no, I think I made a mistake in math.
Okay, so just be careful with these values. I mean, and that's the whole problem. Okay, it's a simple question, but it's the plus and minus signs that's going to mess things up. Now, coming to the last part. The last part is about, I think, drawing the Hess cycle, which is that use your answer to 2 and the data given in the table to calculate the standard enthalpy change for reaction number 3. So for 2, this is 2, right? So now we have the data, which is that we can calculate the enthalpy because we've got, you're going to dissociate it. Okay, so let me get rid of the previous working. Now again, baryamines are going to be dissociated, right? So it's actually 2 OH ions, and you've got 2 CO2s, and the product is what? This is going to be dissociated as well. So it's going to be baryamines plus 2 HCO3 minus 1. So enthalpies of formation are all given. For HCO3, we just calculated. So it's going to be product minus reactants. HCO3 was what? Minus 692 times 2. The other one, the other product is what? The other product is baryamines, which is given above. So we're going to do all the working there. Okay, take your values from the table. So 692 baryamines is what? It's minus 538. Okay, that's minus 538. And then minus the reactant. So it's baryamines again, that's minus 538. You got 2 OHNs, that's minus 230 times 2. And then you've got 2 CO2s, which is minus 394 times 2. So minus 394. So quickly try and solve this one and you'll find the enthalpy change of this reaction. What are we getting? Has somebody completed the working?
I got minus 136.
Minus 136.
Okay, so minus 136. So this
Minus
one is,
136.
okay, this one is minus 136. So this one, the last one was minus 136. So now you've got the last question. He says, you got the enthalpy change for this reaction, which is what? Minus, we just did it. Okay, that's minus 136, right? Kilojoules per mole. Now he's asking in part 4, he's asking what will be the enthalpy change for this reaction? How would the value of delta HR3, which is this one, reaction 3, compare with the value of delta HR4, which is the enthalpy of the reaction number 4? So what would be the difference between these two values? If that's minus 136, what is this then? Anyone, any idea? How would the enthalpy change? Minahil, Lanam, any idea?
Sir, would it increase?
I said it's just a trick question. Basically, it's going to remain exactly the same. Why? Because if you look at the equation, TK, this is aqueous. Aqueous means it's dissociated, right? And then you've got carbon dioxide. And then calcium hydrogen carbonate is also aqueous. That means the ions will be dissociated. HCO3 minus 1 is going to be separate, right? And look at the first equation, barium hydroxide, that's aqueous. So that means it's dissociated. And you've got 2 OH ions. And then you've got 2 carbon dioxides. And then it's barium hydrogen carbonate. It's this one. So that is also dissociated. So it's barium ions and 2 HCO3 minus 1 ions. Now, if you look at both these equations, what you'll notice is that the calcium ion is not doing anything. in the reaction. Like even if you look at the math, enthalpy of formation of calcium ions minus enthalpy of formation of calcium ions, product minus reactants. So that means the calcium ion has no effect on the enthalpy change. Is that clear? It's a spectator ion. And the same applies to the other equation. The barium ion is literally not doing anything in the reaction. You add barium ions and you still have barium ions. So even if you do product minus reactants, it's going to be the enthalpy of formation of barium ions minus the enthalpy of formation of the reactant, which will also have barium ions. So that's going to get cancelled out anyways. So the ions are just spectator ions. They're not doing anything, which means the enthalpy change will be exactly the same. Is that clear? So this one and this one are basically exactly going to be the same. You clear? Is this part clear?
Yes, sir. Thank you. I think we had a question like it yesterday.
Yeah, but that was different. In that question, the value was actually changing because they gave a weak acid. I mean, that question, it was something like this, right? If you remember this. That question was like this. It was Mg plus HCl, and it was forming what? MgCl2 plus H2 gas, right? So over here, the Cl line is just a spectator ion because the HCl is aqueous. So it's going to dissociate. I mean, it's going to produce 2H plus 1, like if it's balanced. And Mg2 plus and 2Cl minus 1, and it's going to form H2 gas, right? So the Cl lines are not really doing anything. So they're not going to affect the enthalpy change. So even if it's nitric acid, the enthalpy change would pretty much remain exactly the same. Except the question that we did last time, there was an effect. Because the next question was about, they were comparing it with a weak acid, like ethanoic acid. So it was going to form what? Magnesium ethanoate? Right? And plus H2 gas. Now, the problem with ethanoic acid is that ethanoic acid doesn't like to dissociate. So even though the reaction is the same, some energy got used up in dissociating the ethanoic acid. So remember, weak acids, when you use weak acids, some energy gets used up while ionizing the weak acid. HCl is automatically ionized. You don't have to do anything. It's already ionized. But ethanoic acid is not ionized. So some energy gets used up so it's slightly more endothermic. Is that clear?
Yeah, thank you so much, sir.
Because that was different. So next one. Thermal stabilities we're not going to do right now. Yeah, this one. Okay, we've got a Born-Haber cycle question. So we're going to construct a Born-Haber cycle and we're going to try and figure out potassium oxide. Okay, this is probably going to be the last. We'll just do a couple of more questions and we'll start with electrochemistry. So Born-Haber cycle, how did we construct the Born-Haber cycle? I told you, is he asking you to draw a fully labeled Born-Haber cycle? I don't think he said anything about it. So I'm just going to skip a few steps. So it's the elements reacting and forming potassium oxide. This is going to be half O2 and this is going to be 2 potassiums, right? Now that's your delta HF. The value of delta HF is already given. That's given over here. That's minus 361. Now what's the other path? The other path is you atomize first. So I'm just going to atomize them in one step. You're going to turn potassium into gaseous atoms and you're going to turn oxygen into gaseous atoms, right? Now to turn potassium into gaseous atoms, that's 89. So that's plus 89 times 2. And how do you turn oxygen into gaseous atoms? What is the enthalpy change? What is the energy that's required over here? What is that equal to? Anyone? They gave me the
Is it
enthalpy of...
the bond breaking?
Yeah, you're breaking the bonds, right? You're breaking the oxygen-oxygen bond. Half moles of them. So the oxygen-oxygen bond energy is given in the data booklet. So that's 496. And you're breaking half moles of it. So that's 496 divided by 2. So that's the bond energy divided by 2. And then you're going to ionize them. So you want potassium to turn into ions K plus 1 gaseous ions, and you want oxygen to turn into ions minus 2 ions. Now, oxygen turning into ions, that's given. That's minus 141 to gain the first electron and plus 798 so that you can gain the second electron. Now, to ionize potassium, that's probably given in the data booklet. So we need to look up the data booklet. It's going to be somewhere over here. Potassium is with K. K is over here. It's given as 418, right? So this value is 418 times 2 because you're ionizing 2 potassiums. And once you have ionized, then that's equal to your lattice energy. So one path is equal to the other path, your other path being this path over here, all of this path. So your lattice energy is equal to, so remember, it's again, be very careful with the signs. So it's going to be what? Plus 141. Everything has to go in the other direction. Plus 41, minus 798. Then you have minus 418 times 2. And then it's minus 89 times 2. Okay, it's minus 496 divided by 2. And then it's minus 361. Okay, so I have to, lattice enthalpy is basically equal to all of this stuff. So what do we get for this? मेहर क्या आ रहा है इसका या कोई और?
I got minus 2,280.
ठीक है, minus 2,280, right? ठीक
Yes,
है.
sir.
Okay, so we've kind of done enough questions. We already did a lot of lattice energy questions earlier on, and we've done these other questions. Remember, it's all connected to your AS energetics as well. We did this question as well, where we found out the lattice enthalpy of MgCl. Okay, this was earlier done. So you can try and practice more questions. We did a lot of lattice energy questions. So we're going to move to the next topic. And that topic is, let me get rid of this. So the next topic we're going to do, that's going to be electrochemistry. That's more to do with redox reactions. In AS, you didn't really do a lot. Okay, a lot of your syllabus, 90% of your syllabus is basically part of A levels, right? In AS, you didn't really do much. Now, we're going to start with basics, right? We're going to start with redox reactions, which you've already done, covered in O levels and as well as in AS as well. So what's a redox reaction? That's a reduction process and oxidation process. Reduction is what? Reduction is basically a gain of electrons. And oxidation, so by definition, reduction is a gain of electrons only. And oxidation is your loss of electrons. And that's it, no other definition. There are other ways of knowing whether reduction and oxidation is happening, but that's not part of the definition. Okay, so definition is that it's a gain of electrons and the other one is a loss of electrons. So the other ways of knowing whether something is getting reduced or oxidized, that's when something is gaining H atoms or it's losing oxygen atoms, right? Remember, a gain of H atoms translates into a gain of 1 electron. Okay, I'm going to explain why it means a gain of 1 electron. And a loss of oxygen atom basically kind of means, so when something loses oxygen, that kind of means it's gaining. It's a gain of 2 electrons. Okay, I'm going to show you why that means, why does it mean that? And the other thing is the reverse, which is that oxidation is a loss of H atoms. So when something loses H, it loses basically loss of one electron. And when something gains an oxygen atom, remember, not an ion, an atom, right? That means it has lost 2 electrons. Okay, so that's it. So anyways, you're already familiar with this. Okay, you're probably not going to be familiar with why it means a loss of electrons or why does that mean a gain of electrons, but we're going to talk about it later on. When something is getting oxidized, what happens to the oxidation state? It increases. So if you have all the charges, 0 in the middle, this is +1, +2, +3, and so on, +7, +8. And then you've got -1, -2, -3, and so on. So the higher you're going in that direction, that means oxidation. That means you're constantly losing electrons. You're going in the opposite direction, that means it's going to be reduction. So if you're going down, that simply means you're reduction. That means you're gaining electrons. So very quickly, can somebody tell me what's happening over here? Like if Al goes from -3 to -1, did it lose electrons? Did it gain electrons?
It lost electrons.
Okay, so you're going from -3, you're going upwards, right? -3 to -1. So that means it lost exactly how many electrons? 2 electrons, right?
Oxidation.
So that's oxidation, okay? And secondly, if you have, let's say you've got Cl +7 and it changes to Cl +3, right? So that means what?
That's again lower reduction.
Kitne
4 electrons gain.
It gained 4 electrons and that's reduction, okay? So you're clear that this is very basic stuff. Is this clear?
Yes, sir.
Okay, so clear, no questions, right? So oxidation reduction. Now the first thing is when someone gains electrons, you know that it becomes more negative or it becomes less positive. It just goes downwards, right? Its charge becomes increasingly negative. When something loses electrons, its charge becomes increasingly positive. Now, the very basic thing is what's an oxidation state? Okay. So what do we mean by an oxidation state? So the oxidation state is it's the charge on an element in a compound or an element or just a charge on an element. But in a compound they get a charge. So in a compound, if the compound is ionic or if the compound is treated like an ionic compound, so not all compounds have charges. So what this is that you're going to treat a compound as if it's ionic. And the reason is, for example, if I have NaCl, now Na is actually +1 and Cl is actually -1. It's a -1 ion and Na is a +1 ion. There's a huge difference in electronegativity. Na is the one that's losing electrons, Cl is the one that's gaining electrons, right? We already know this. You know this from O levels. So Na is +1 and Cl is actually -1, right? So it is an ionic compound. But what if you have, and I'm going to write this down. So someone is actually gaining electrons. So there's a gain of electrons over here and there's a loss of electrons over here, which is actually happening. But if you have a molecule of HCl, then they're not actually gaining or sharing, they're not losing or gaining electrons. No one has a -1 charge. They're not forming ions. It's a covalent molecule. So why do we say Cl is -1 and why do we say that H is +1? The reason is we're going to think of it as an ionic compound because if you look at the electronegativity table, like if I have the Pauling scale values, remember the Pauling scale table gives you the electronegativity values of different compounds. So let me see a table with values in it. That's good enough. So we've got a table and it's got electronegativity values. Let's just keep it till this part. So now the idea is, now you're pretty sure that electronegativity, I mean, I'm sure you already know this, that what happens is that electronegativity values, they increase when you move to the right. So your electronegativity increases. The tendency for an atom to gain electrons increases when you move to the right. Why does it increase? Because you've got more protons, right? The atom has more protons and it has the same number of shells. So shielding is constant. The other factors are not really in play. Shielding is. So there's a much stronger attraction for electrons. So that's why the atoms on the right side, they become more and more electronegative. And similarly, it also increases when you go up the period, up a group, that it increases. They become more electronegative because smaller atoms are less shielded. So they are less shielded and they are smaller as well. So they're going to have more attraction for electrons, which is why smaller atoms are going to be more electronegative. So that makes fluorine one of the most electronegative elements out there. So now coming back to this, I told you that HCl is a covalent molecule, right? Why is it a covalent molecule? Why are molecules covalent to begin with? Molecules are covalent because the difference in electronegativity is not huge. Like, for example, if I have two Cl molecules, right? Both Cls are trying to pull electrons towards themselves. But both Cls are equally trying to pull the electrons towards themselves, which is why the electrons, they get stuck somewhere in the middle, right? No one is able to gain or no one is able to lose electrons, right? So you get a covalent molecule when let me tell you this in detail. You get an ionic molecule when the electronegativity difference, I'm just going to write En. What was the electronegativity difference? If it was very high, if it was specifically, it was greater than 1.7, right? Your compound was supposed to be ionic. Someone was going to lose electrons and someone is going to gain electrons if the electronegativity difference is high. Like if I pick any element, if I pick potassium and bromine, right? Bromine is like 2.96, potassium is 0.82. The electronegativity difference between them is like really, really large. Okay, this is 2.96, this is 0.2. If you take the difference, that is a lot greater than 1.6. So potassium bromide is going to show ionic properties. What are ionic properties? Ionic properties are that it's going to form an ionic lattice, right? It's going to form a bunch of ions. And so there's going to be positive ions, there's going to be negative ions, and they'll all be strongly attracted to each other, just like NaCl. So it's going to form positive ions, negative ions. Negative ions will be attracted to positive ions. So it's going to form a giant ionic lattice. And you know the properties of ionic compounds, which is that they normally have high melting points and they are soluble and they conduct electricity when they are molten or aqueous, right? So, but for ions to form, the difference has to be really, really large. And you can predict the properties by just looking at the electronegativity values. Like potassium bromide, it's definitely going to look at potassium bromide, right? Potassium is here. Where's potassium? 0.82. Like if I Google potassium bromide, and I just checked the melting point of potassium bromide. I'm pretty sure it is ionic. So if I just Google its melting point, that's coming out to be 734. That's pretty high. So definitely ionic. It's definitely a bunch of positive ions, negative ions, all attracted to each other. But if the difference in electronegativity is less, like aluminium chloride, aluminium is 1.61 and Cl is like even aluminium bromide, and Cl is 3.16. So what's the difference in the electronegativity? That's kind of low. It's less than 1.7 or close to 1.7. I think it's less than 1.7. Kya, what's the difference between these two?
1.55.
Okay, so that's less than 1.7. So that means they'll not be able to form ions, right? Aluminium chloride, that's the difference is not that high, so it's not that large. So one of the atom will not be able to gain electrons, right? So that means it's going to have more covalent character. That means it's going to have low melting points, right? So if I look at the melting point of AlCl3, that's like 180. That's like very low. Okay. So by just looking at the electronegativity difference, I can figure out whether the substance is going to be ionic or covalent. Now the ionic compounds have charges. They've got ions. They're going to form ions. What's going to happen with HCl? The thing with HCl is that it's not going to form ions. It's just going to be a covalent molecule. And since they're not forming ions, there's going to be another HCl molecule, which is why they're going to have weak intermolecular forces between them. They're not going to attract each other, which is why the melting and boiling points are going to be low. So the last thing is, why do we say that H is +1 and why do we say that Cl is -1 when in fact it's not, right? So when it comes to oxidation state, we do say that Cl is -1. We do say that H is +1. The reason is that when it comes to oxidation states, we don't really care whether ions are getting formed or not. We just care about the fact who's gaining electrons and who's losing electrons. So if you look at HCl, H is what, 2.2? And Cl is what, 3.16? Now it's definitely going to be covalent because the difference is not very large. But the electrons are going to be closer to one of the atoms. So which side will the electrons be closer to? कौन सा atom होगा? It's going to be a polar molecule, right?
Cl.
Okay, so it's going to be Cl, right? So Cl. So even though Cl is not fully gaining those electrons, it's just going to be a very slight negative charge, and H will be very slight positive charge. But we don't care. We don't care whether they form ions or not. When it comes to redox, we just care who's the one who's gaining those electrons and who's the one who's losing those electrons. Even if they're doing it partially, we don't care whether they're doing it partially or whether they're doing it fully. So when it comes to oxidation state, you treat it as if it's ionic. You're going to say that this is -1 and this is +1 because we don't care whether they form ions or not. We just care between an H and Cl, who's the one that's gaining electrons, even if it's partially gaining electrons, and who's the one who's losing electrons, even if they're doing it partially. Okay, is this clear?
Yes, sir.
So that's oxidation. That's oxidation state. You're going to treat every compound as if it's ionic, right? Because we basically don't care whether they form ions or not. So if I have oxygen and fluorine, right? So if you look at the Pauling scale table, it's fluorine is a lot more electronegative, right? It's 3.98, and this is 3.98, while oxygen is what, 3.44, right? So who's the one who's gaining electrons and who's the one who's losing electrons? The electrons would be closer to fluorine, right? So fluorine is the one that's going to be -1 and oxygen is the one that's going to be +2. Is that clear? Is this part clear? This one.
Yes, sir.
So basically, so that's about it. So basically, oxidation states are you treat every compound as if it's ionic. Okay, and that gives you an idea about who's going to gain electron and who's going to lose electrons. So remember, this is your backup. If you ever get stuck with oxidation states or finding oxidation states, For example, over here, if I have a molecule, I mean, there are simpler methods of finding oxidation states. This is the most difficult one. We're going to study the simpler ones tomorrow, which you already know. Can you quickly tell me, the oxygen is more electronegative than H, right? So these electrons are what? Closer to oxygen, right? So oxygen will be -2, right? So between C and H, who's more electronegative? C is 2.55, H is 2.2. So C is more electronegative. So these electrons will be closer to C. So this is +1. And these electrons are also closer to C. So this is +1. So what is the oxidation state of C over here in the middle? It gained how many electrons? It gained 2 electrons and lost how many electrons? It also lost 2 electrons, right?
2.
So end result क्या होगा? It's going to have it's going to be 0 oxidation state, right? Okay, so remember, this is your backup. You're not going to use this method, but that's your backup. Okay, if you ever get stuck and the other method doesn't work, then you can use this method. Okay. So you clear it? So we're going to try and do balancing redox equations tomorrow then. Okay.
Okay, sir.
So let's continue to Monday then. Okay, let's continue on Monday. Okay then. Take care.
Okay.
Yes.
Thank you, sir.